Just a quick introduction who I am. I'm by trade a physical oceanographer. I'm interested in the role of the ocean in the Earth's climate system. And sort of within the last couple of years, I've increasingly realized the value of open source development and open science in general. And I just also want to briefly acknowledge that none of the work I'm showing here, not a little bit, would be possible without the scientific Python community and my many, many collaborators. So big thanks to everyone for contributing. So I like to motivate my work with like sort of the elephant in the room. The changes to the Earth system caused by human activity, I believe, will be the defining issue of our time. And the scientific evidence is clear, and we unequivocally know that we need to reduce emission of greenhouse gases as fast as possible. I would also argue that we really need to turbocharge Earth system science now to provide the best information for mitigation and adaptation. And really one of the few positive things in this regard and in this topic, I think, is really the amazing work that the Earth science community has done in the past decades. And sort of one example of this is maybe a simple looking plot, but it's really amazing that we can show something like this, right? Like this plot shows global average sea surface temperatures. This is a plot from the IPCC report, and this shows sort of the observed heating of the planet and then basically the projections under different scenarios that people have come up where we basically have sort of reduced emissions and like business as usual and cases in between. And sort of this shows nicely the elements that we need, I think, for most topics in Earth science. We need some observations, right? We only have one iteration of this planet, cannot run it again, and we need to record as much as possible. The other thing we really need is models, right? We only have one way to project future changes. There's no lab planet that we can run with a controlled experiment, so we have to do it in a computer. And when we tie all of this together with theory, then we really sort of create scientific knowledge, and this is sort of the kind of stuff that ends up in the IPCC report as a synthesis. And really, like, whenever I look at like visualizations like this, this makes me really happy pretty much every day when I work and look at something like this new coming out. These like beautiful, rich data sets, right? It's a huge motivation to do the work that I do every day. But there's sort of one caveat: with more models and more observation, we also get a lot more data to process, right? This is just showing the NASA data archive and projected changes with like two very high resolution satellite missions coming up. And generally, I would argue, and I think a lot of people will probably agree, that sort of at the current track and future current and future modal simulations will really grind traditional analysis workflows to a halt. I think it's important right here, like when I give talks in the Earth science community, everybody always knows, but it's important to say that a climate model here is really like a big numerical simulation of the full planet. So we're basically chopping up the planet and its different components, the ocean, the atmosphere, land, et cetera, into boxes, and then use our knowledge of like physics, biology, chemistry to sort of integrate that forward in time, and that gives us a projection of certain quantities that you're interested in. These models have been sort of steadily advancing in resolution and complexity over the years. And this leads to projections of more and more details, right? Like more regionally accurate estimates and things like ecosystems in the ocean and on land. And this really increases the value to more and more people outside even of the climate science community. So like industry, other stakeholders think like these projections become more and more relevant and valuable. Just a quick clarification, this talk is not actually talking about running these kinds of climate models, it's about analyzing the output. The data production and dissemination is actually something I think that works really well. I think the struggle I have, and that many of us have, is actually analyzing the output. So the climate model projections are really like a distributed global effort, right? Like you have different modeling centers. Each of these centers is like around the world, and they use different codes and different implementations to run these climate models. And then the Earth System Grid Federation distributes them to the users. And these are sort of packaged in netcdf files usually and follow the CF conventions. So there's a lot of cleaning up already done, and there's sort of the big advantage of this is we really can sort of sample the uncertainty of these projections. But the disadvantage is that, well, if you would produce all of them in the same modeling center, they would be more homogeneous data. But like, I think the advantages sort of outweigh the disadvantages, that we really have sort of different approaches, different people working on these things, and you sort of have a variety of projections and can really sort of address uncertainty in the system. I do, however, think that sort of the traditional workflow needs to be rethought a little bit. But like generally, the workflow that we follow is we download some data, we then sort of clean and combine it, because like there's been a tremendous effort, and I want to acknowledge that, by the ESGF community to sort of homogenize this data, but to really sort of analyze it in one go. There's still, you know, a little bit left at the end that we need to correct. And then you basically want to crunch the data and interpret the results. But, you know, especially the first two steps become highly problematic if the amount of data really increases. So the first one really is the big one, like the download. You know, on a basic level, no one wants to wait for downloads. But, you know, if it's like a couple of minutes, then that's not that bad. But like, this is not even really a joke. Like, I've personally waited for certain data sets and for like a set of stuff for almost a month to download and get to that data to analyze it. So that's obviously like too long. I don't know. I generally lose interest after a couple of days on things, and I think others are probably the same. And so on a first hand, it dampens scientific curiosity. You know, who knows what I'll be interested in a month. But it also really sort of, it isolates who can work with this data. It's like, effectively means that mostly Western large institution will sort of, like my employer, Columbia University, will create a data fortress for their employers to download. So they download it to their file system, to their HPC, but that's not open to the world, right? Like, it's only open to people who collaborate with me or people who are also at Columbia. And it's also pretty wasteful, right? Like, if you think about this like at a petabyte scale, if every institution keeps like duplicating this, like, it's a pretty big waste of space. But I think really the main issue for me with this is that it excludes people from contributing to climate science and sort of participating in the climate discourse. Then we come to the clean and combine effort. As I said, sort of despite the amazing efforts to homogenize the data, there's still some things to clean up. There's like namings that are not quite homogeneous. And the problem with this, I feel like that in a traditional workflow and stuff that I've done myself is sort of, it's delegated to a grad student or a postdoc who, you know, spends their brain power on implementing something, and maybe different people implement slightly different fixes to something that is sort of a problem for a whole community and should really be sort of centralized in one place. And then you come to the actual sort of crunching the data step. And that sort of, you know, really depends on the tools and the resources available, how fast this is going. But it can also be a major time drain. But that's a real problem, right? Because ideally, you really want to have this go fast so that you can, like, in an agile way, actually iterate these things. I think nobody has ever like come up with an analysis and then like printed it and says like, yep, done. Paper submitted, right? Like you go back and through that loop. If you can go through that loop more often, your results are going to get better. At least I believe that. And just to sort of acknowledge this, I don't want to like discourage this workflow. I think it's just like we need to move on to like a more modern workflow. This has produced a lot of amazing science over the years, right? But it really isn't ideal as data grows, and that's what we're experiencing. You know, this is sort of like where you spend most of your time in, I would say, the current workflow. And really what we want to do is exactly the opposite, right? And so what we've been working on is a cloud-native workflow that sort of tries to stack the pyramid in the opposite way. This really lets you focus on science and like do agile science and really try out and refine ideas. And it lets everybody participate. So the base of this really is getting that data from ESGF into a analysis-ready, cloud-optimized format. And the Pangeo community has partnered with ESGF and uploaded a substantial amount of the CMIP 6 archive, both to Google Cloud Storage and Amazon S3. And this is publicly available, so you can access that on your computer if you have internet. And also bring, obviously, like more performant compute to that. And then the other half, I think, is sort of this sub-part of the Pangeo stack. Really, these are sort of the main libraries that make this work. Obviously, there's many more connected to this, but these are sort of the ones I want to point out. At the bottom really is sort of ZAR for an efficient, fast access to arrays and object store. And then on top of that sits Dask that really enables easy parallelization and makes that sort of data crunching and actually looking at the results loop go faster. And then in the middle is Xarray, sort of the sort of flexible scientific data structure that then sort of enables a lot of other packages to sort of plug into that. One of these packages is XMIP. That's basically my approach to, or my attempt to do sort of crowdsourced cleaning and combining of this specific data set, these large sort of model intercomparison projects. And then when it comes to the analysis, like then you're open. There's like many amazing packages in the Pangeo stack that you can then plug into these things because they all kind of work with X-array data sets. But enough of the talking. I would like to try to give a demo and just reproduce that plot right here for you now. I will have to change these settings here, so bear with me for a second. Okay, I hope this hasn't died. I've taken the liberty to set up a local cluster on this cloud deployment. This is one of the Pangeo cloud deployments. You can sign up for that on pangeo.io and click on cloud right now, and then you can actually go to the repository that I did not show long enough. But like, if you find it, you can run it in parallel. And then we're basically need to import a couple of functions. I'm going to go through this relatively quick, and I apologize for that. Happy to like answer any question and like go through this later, but I really want to go to the actual step. Then we're the idea here is just it's a sort of search for these data sets by facets. So it's really just all at the moment stored in a CSV, and this is something we actively are working on to make that a bit more sophisticated, because that's clearly like a bit of a low-tech solution. And then what I'm doing here is basically defining a subset of data. I'm unfortunately wasn't able to like process all of the models. There's about 80. So I've chosen a subset that doesn't have too many members, and sort of a good dozen or a bit more of them. And then I'm choosing basically these, what is important here, these experiments, like historical and these SSP scenarios for different forcings. And then what I'm loading is the sea surface temperature encoded as TOS. And what we need for this calculation, and that's sort of an important part in this workflow, is we need this cell area, because these are not uniformly sized cells in each of these numerical models. So if you want to have an actual accurate globally weighted average, we need to load the area and weight by that area. So okay, while I was chatting, this has loaded. I think we can still optimize this to get faster, but like, downloading these data sets would definitely have taken longer than like this session. And so now we have them lazily loaded into our notebook, and now there's some things from XMIP. Basically what we're doing here is we have a dictionary of a bunch of X-ray data sets. Some of them are sea surface temperature, some of them are areas, and we're just matching them together based on metadata attributes. So like XMIP, basically the whole thing works on these facet attributes that identifies each of these data sets. And then what I'm going to do again to like speed this up a little bit is for many of these models, you run different ensemble members with slightly perturbed initial conditions to get a sort of handle on internal variability in the system. But like we're just going to trim this down. Like if you want to run through this, you can do this with all the members, but you need to have an average step in there. And then what I'm doing here is like, this is the analysis, and this is like, I love this line. This here is just, this is why I love X-array. Whoops, this is why I hate Apple. But so you're basically creating this average time series here, right? What is happening? We're looping through these and getting like data sets from all of the different modeling centers. We're taking this data array, that's sea surface temperature. We're using the weighted function and then plugging in the corresponding area. We have to fill the missing values with 0. And then we're taking a mean over X and Y. And this is actually something that I glossed over a little bit, but being able to do the mean over X and Y is something that XMIP also enables with a pre-processing function that I've inserted here very sneakily, because some of these models would have, for instance, have an I and J index there. It's just a simple naming thing. But so basically, that's it, right? I'm reattaching the attributes here. I could have set that in a context manager, but like, whatever. So we're just reassigning this to a new dictionary. And I'm seeing, this is something that happens sometimes to me. I'm sorry. There's a little bit of the DAS coming. All right, we're getting the tail end of it. Sorry about that. Basically, we're just like, this can also be more efficient, but like for now, I'm just looping through them, and like Dask is happily chugging through this on like the 16 cores that we have on this machine. And we're almost done here. I think TiESM is always the last one. No, it's not. That's how we just have to wait a little bit. But like, I just want to point out that this kind of stuff usually, right? Like I would spend days on this, right? This would be like submitted to some batch system, and like crawl through that, and just like even getting to this step here would have taken usually days, and I've gone through that myself. And so then what we're doing now is really purely organizing for the plot. Right? You can go through this in detail, but basically what I'm just doing here is like, hey, is this part of the historical run or one of these SSP runs? And it's just, there's better ways to do this, but you know, for the sake of brevity. Then what the plot actually, if you notice that the plot was sort of centered around 0, and this was in reference to an anomaly, to a base period that we have to calculate from the historical run. Again, well, this is a bit, this is, again, beautiful X-array, right? We're defining this base period as one, as sort of a, this is now concatenated over different models, and we're defining a smoothing window, and we're just like having a smooth time series of this for each of these scenarios, and then we're just going to go ahead and plot it. And there you go. There we have a plot. There's like start to end. Oh, that's very nice. Okay, we gotta quickly go back to this. Maybe a sleeker way to do that. All right, and we're back. So here, just for comparison, the original plot, sure, we can adjust the colors a little bit, and you know, there's not all members in there, but I think it's pretty nice that, you know, it's also not all models in there, but I'm pretty convinced that if you actually include all of this and spend half an hour on it, you get to something that is very, very close. And so, I guess I went a bit fast. Didn't expect that demo to go that quick. Well, more time for questions. That's good. So really, I want everyone to like take this as a motivation to really start exploring CMIP data. I hope that these tools, and you know, this is all work in progress. I think what I've just showed is really a prototype of the cloud deployments, a lot of the software. But I think what I want to say is this works, right? Like I've used this stack to actually do science, and the paper's almost published. That's why I didn't quite put here. But this is not just a toy. I truly believe that we can do climate science this way, and that way you can basically sort of skip the step of, you know, asking the author for the actual analysis code and not just the plotting code, and like some, you know, you can basically fork in at every way of the analysis workflow, fork it out and do your thing. Just take your favorite models, do some other, I don't know, smoothing approach, or you know, you name it. And you can get in there and sort of do the science without sort of having that toil period to set it up, just like other people have done it before. I really think that this is sort of, I think one of my foci is sort of getting more diverse perspectives on this data. That means more people from different places around the world, but also people from industry, people from different fields. We need to get more hands on this data. I think it's notoriously underanalyzed, and you know, we're facing this climate crisis. We need people, all hands on deck. And you know, faster stuff also gives us the opportunity to maybe actually reduce our current emissions as fast as possible, which is always important to emphasize that is sort of the first thing we all need to do. As a last one, if you run into any issues with this, please raise a hand on XMIP. And also, if you're interested in working on this, this is not quite the community project that I wanted it to be yet. So I'm very happy to like welcome everyone to like join in and improve the code. And basically, one of the things is just use different data sets. This is basically like the more data sets I get in contact with, the more fixes I build into this. And I think then it sort of percolates to the other user base. Otherwise, please feel free to reach out about this or other stuff. I'm very keen to connect with folks, and yeah, I can take a few questions, I guess.
So yeah, we have a few questions listed here. So the first one, excellent talk. Your project looks similar to what Google Earth Engine and or the Climate Engine project is doing. Has your team collaborated with them?
I mean, I think this goes back to sort of this idea of like a pre-built platform versus a very modular system. I'm not personally that familiar with Google Earth Engine, but like what I've seen so far is pretty amazing. But I think the decisive factor here is that it's not the users or the scientist or whoever wants to work with this data that actually determines which data gets loaded in and what sort of tools you can apply to it. From my experience, that it's like very important for climate scientists to have these sort of creative approaches that are not pre-baked in a platform. So I think that was the reason to modularize this a bit more.
The next question, what was the DAS cluster at the back? How many workers?
It's one worker on like 16 threads, I believe. And it's just like basically one of the deployments we have on the Pangeo hub. I could have run this in a DAS gateway with even more workers, but like for the sake of like keeping the demo safe and not having more moving parts, I chose to do this. But you can definitely do this even faster.
Alrighty, next question. What do we need to do as a community to entrain more scientists to use these kinds of workflows?
Interesting question. I mean, I think this is very sort of opinionated piece from you. Other people might have other opinions. I think what you can do as a PI is encourage your students to use these kind of tools. I think that's an important part, to sort of train a new generation. I think other than that, we can just do stuff like this, right? Like we're showing that this actually works and that you can do it in an afternoon rather than a week. I hope that convinces people.
Next question. Sorry if I missed this, but is the entirety of CMIP 6 available on the Czar Cloud Store?
Excellent question. No, it's not. And this is again, sort of reflects a bit of the prototype character of this project. What we have right now in Google Cloud Storage is a part, like sort of very highly requested data sets, but we are actually working on a more automated way to bring user-requested data to the cloud. That's not quite ready yet, but it's something we're working on in conjunction with Pangeo Forge to really automate that process. Happy to provide some more links for that in the chat.
And then, do you have any recommendations for resources for people wanting to get started with this?
Oh, absolutely. I'll post them in the chat. I think there's like the Pangeo website. There's the Pangeo CMIP 6 website. And yeah, I did kind of omit these, and I'll put them in the Slack chat right away afterwards.
Alrighty, do we have any other questions? Any from the room? Looks like we got another question. So what is the biggest, so awesome talk, thanks. So what is the biggest challenge that you face today?
I think like just basically I need more people to use this data. I need more people to discover edge cases. That's the biggest problem. It's just like I want people to like sort of, you know, like there's people who want the paleo data and like something I've never worked with, and like we just started working with them. And you find an issue with the time dimension, and that has been, you know, there's something in progress for the pandas type. But like I basically just need input from people where they're stuck. I think that's sort of for this effort.
And then one other question. So I noticed on here that it says XMIP, but then on the right it says CMIP 6 pre-processing. Could you kind of talk about like what renaming a project is like and kind of that whole process?
Well, the biggest lesson that I learned and sort of the night before flying out to Austin, and yeah, I've definitely procrastinated this, but the biggest thing is check that your name is available on GitHub, SciPy, and Conda Forge, because I somehow assumed that there will be no one who has the SciPy package without a GitHub name, but there was, so I had to like go through some iterations. Other than that, yeah, there's this was a very recent sort of event to reflect a little bit. I think me getting sort of tongue twisted around saying CMIP 6 pre-processing too much, and the fact that I noticed that the capabilities of this is actually extending further than both CMIP 6 and also extends to other model intercomparison projects, something that I learned later, so it's just a bit more snazzy, but behind the scenes it's pretty much the same. But yeah, renaming, I have some notes that I wrote down. Maybe I should actually write a little blog post about that.
Another question. So what would you say was like the most difficult part of this process?
I assume this means the demo, or just that workflow. I mean, this is, again, I'm standing on the shoulders of many giants here. I have not done all of this. I think the difficult part about this is actually how to keep this whole thing alive and paid, and that's something I'm haven't worried that much about. But I think that's sort of how to get these kind of systems funded in a long-term fashion. I think I would identify as like the biggest issue. And there's other people in the room who can probably talk to that a bit better. But like I think that's.
Sorry about that. That was the original timer. Do we have any other questions? No? All right. Yeah. Question?
How much scope do you think there is for, like, when you download that data, like, what really how much scope do you think there is for, like,
Yeah. So the question is about the scope. Yeah. If you do want to come up here and ask a question, just that way it can be in the microphone.
The question was just, when you're downloading the data, what's the interface like for, because the CMIP's made of like huge numbers of different models with like subtle variations between them grouped by experiments. Like what's it like at the moment as an interface to download that kind of data, and how could it be better?
Oh, that's an excellent question, and I think that's something that goes together with like the kind of work we're doing with Pangeo Forge. I think that I would probably punt that to the Pangeo Forge side and hope that, and I know they're working on like an awesome front end catalog for these kind of data where you can basically filter after these facets. So like the essential part in these data sets is like these facets which describe different models, different members, different experiment IDs. So you have like this like n-dimensional sort of like ordering of these data sets, and you need to be able to filter between them. Right now we have a big CSV, and you can do that with just some pandas, and you can filter certain things out, and you get a bunch of ZAR stores and load them in. But yeah, that's all quite hacky, and so yeah, I think that like a good front end connected to something more established is probably the solution to that. Thanks, Tom.